York University since 2005, but he also worked for University of California in Santa Barbara, Haverford College, Exxon Research and Engineering, and University of Pittsburgh. Currently, he studies the complex fluids, focusing on self-assembly. Precisely, his lecture for today is colloidal self-assembly. Please have the time.
Okay, thank you. It's a pleasure to be here again. So I'm going to start today's talk with a movie. This is a movie that was made, 50 years ago maybe. So what we have here is a Couette cell. So what it is there's an outer cylinder and an inner cylinder, and in between the two is a gap that's filled with a viscous liquid. And there's this handle attached to the inner cylinder so that you can rotate it, which shears the liquid in between. So let's watch what happens here. This is actually G.I. Taylor doing the experiment, and he's introducing a drop of the same liquid but dyed red so that you can see what happens to it as it's sheared. So as you can see here, he goes around 4 times and shears that red drop out into a thin ribbon. And then he reverses the flow. And you see that the drop reforms. All right. So this is a vivid demonstration of a well-known property of low Reynolds numbers flow, namely that they are reversible. So the flow of liquids is governed by Newton's second law, like everything else, which is written here as the Navier-Stokes equation. Acceleration times mass is equal to the forces acting on the system. At a low Reynolds number, the inertia is unimportant. All right, so this happens when the viscosity, represented by eta here, is very high relative to the velocity times some characteristic length scale times the density of the fluid. So when that number is much less than 1, you can ignore this inertial term, and you just get that the sum of the forces has to be equal to 0, and together with this condition on the velocity, which just says that the fluid is incompressible, you have essentially a set of linear partial differential equations that lead to this reversible behavior. My best estimate is that the Reynolds number in that experiment we just saw was about 0.03. Now, the question that we set out to answer today, or that a few years ago actually when we started this work, was what happens if you add particles. So what I mean by particles here is I actually mean fairly large particles, that are suspended in the liquid, and if you shear them, it turns out that the Stokes equations still apply. All you have to do is apply no-slip boundary conditions at the particle surfaces, but when you do, you find that the particle positions are slaved to the fluid. Now, there's something I want to make clear. Clear here. I'm going the wrong direction with this. And that is that we're dealing with large particles here. The particles are about 1/4 of a millimeter in size. The viscosity of the solvent is about 1,000 times that of water. And so if you calculate the time it takes one of these particles to diffuse its own diameter under Brownian motion, you discover that it takes more than 100 years. All right, so in these experiments, diffusion doesn't matter unless you want to stick around for a couple hundred years. So as we start shearing the plates, say the top one, like this, first of all you define the strain, which is just this x displacement over the gap. So that's going to be an important variable, so pay attention to it. But if you strain the fluid and then strain it back to its original position, the particles can go back to their original position as you would expect. So the question we really set out answer is how sensitive is reversibility when there are not just two particles, but there are many particles. Now, one thing that stimulated this discussion and this question was a series of experiments done by a number of researchers dating back at least to the 1960s. Here I show you perhaps the most complete and recent one by some experiments by Breedveld for his PhD thesis. And what he did is he took some similar particles, put them between two plates, and sheared the top one, and then followed the motion of an individual particle. And when he followed the motion of an individual particle like this, he saw that the particle sort of moved around because of the crowding by its neighbors, having to avoid them that leads to this sort of path that looks a little bit like a random walk. Now, the mean motion of the fluid is just described by this equation. It is delta x is the shear, the strain, times delta y. The velocity is the rate of strain times y. Now, what he discovered is that if he subtracts off this trivial shearing motion and looks at the motion that remains for the particles, he found that the mean square displacement in each direction increased linearly with time. So delta x squared, delta y squared, delta z squared, all increase linearly with time. This relationship, of course, is the hallmark of diffusion. And diffusion, as we all know, is an irreversible process. So we're faced with a conundrum here in that the equations of motion, the Stokes equations, which we have no reason to disbelieve, saying that the motion should be reversible, but the fact that individual particles in a crowded environment seem to follow a diffusion equation suggests that it's irreversible. So we set out to look at this question. So the experiment that we set up looked like this. We have a cuvette cell, just like GI Taylor. Here's our sample. We use roughly 1/4 millimeter polymethyl methacrylate spheres. They're in a solvent that is density matched to the spheres, and is also a refractive index matched to the spheres. So what that means is the fact that it's density matched means that the spheres neither sink nor rise in the fluid, and the fact that it's index matched means that it's transparent. You can't actually see the spheres. The solvent viscosity is about 3,000 times that of water. The Reynolds number we're careful to maintain at 10 to the minus 3. So we maintain very, very low Reynolds numbers. So the Stokes equation should apply. Then what we do is we dye about 1% of the particles black so that we can follow them. So what I show you subsequently, you should remember that you're only seeing 1% of the particles that are actually there. And then what we do is we stand over here with the camera and we shear this inner cylinder back and forth. So if you look at it from the top, this is what it would look like. You see the inner cylinder going back and forth. And this is, while this is just a cartoon, what it's meant to show is that if the particle trajectories, if everything's reversible, the particles should trace out the same trajectory back and forth under this sinusoidal straining motion. So if you look, if we stand over here with our camera and look from the side, this is what we see. And of course, these particles that are moving the farthest are the ones that are farthest away from you. They're the ones closest to the inner cylinder that's moving the most. All right, so you can see that the motion of the particles is quite large. So what we do to test the reversibility is we strain this back and forth like this, but we take a picture just once per cycle at the same point in the cycle each time, at the same phase. If the trajectories are reversible, then we should see the particles in the same place at the same part of the cycle each time. So here is, I'm going to show you a movie that's running. This is a movie where I'm only showing you the particle positions once a cycle, and this is for a strain of 1. Aside from a small drift, because this is actually the very first experiment we did, which is just an experimental see that the particles more or less come back to their same position each time, all right, meaning that this flow is reversible. Because remember, each one of these particles is moving quite a distance to the right and then back to the left. Now what we do is we repeat the same experiment, but this time we increase the strain amplitude to 2.5. All right, so here it was 1, meaning that the inner cylinder went 1 gap width to the right, 1 gap width to the left, and back and forth like this. Now we're going to increase it so that it's 2.5 times, and then 2.5 times that way. And what we get in this case is this. So here you see that, in fact, the particle trajectories are not reversible at all. In fact, they superficially, at least, look like they're executing something a lot like random Brownian motion, for those of you who've seen that kind of thing before. We can follow the trajectories of the particles in time, record their positions with a computer. We can do this for 100 particles or so for many hours, typically. And what you find then is if you calculate from those trajectories, say the mean square displacement as a function of time, and here we're just using the cumulative strain as the dimensionless time, you get a straight line. The higher line is for motion along the direction of the velocity of the fluid, and the lower one is for motion perpendicular to the fluid. So what you get is you get that the irreversible motion is indeed diffusive. It diffuses a little faster in the streamwise direction than it does perpendicular to the streamwise direction. If you plot the diffusion coefficient measured in this way, as a function of the strain amplitude, what you see is that at large strain amplitudes, you get a finite diffusion coefficient, but as you decrease the strain amplitude, the diffusion coefficient gets smaller and smaller. Now, one thing we checked was to see if the diffusion we measured depends on the Reynolds number. And here I show you a couple data points where we have a Reynolds number equal to 0.001, in other words, 0.005. And what we discover is that the Reynolds number makes no difference as long as the Reynolds number is much less than 1. The other thing, of course, that's quite striking about this is that there's a threshold. Namely, that the diffusion coefficient goes to 0 at some finite strain amplitude. And then down here, where the diffusion coefficient is 0, that means that the system behaves in a reversible manner. Okay, so the first question that comes up is why is there a threshold for this irreversible behavior? And we puzzled over this a long time, and my colleague Paul Chapin came up with a simulation that was very helpful in understanding why it is that you get a threshold. So the simulation is very simple. Here we do it in 2 dimensions. So what you do is you take a bunch of particles and you throw them down onto, say, a rectangle. So they're just distributed at random. Now I can illustrate the algorithm down here with just 3 particles, it might be from up here, that are near each other. So the way the algorithm works is you take the system, you strain it, and then you unstrain it. All right, so here we see it strained by gamma naught, which is just B over A here. Actually, it's A over B. What's happened here is because of the strain, and the particles just follow it finally, these 2 particles bump into each other as defined by these circles. So you can think of these circles as some interaction distance. And so it has a sharp cutoff, and the rule is that if the circles around these points overlap any time during this shear cycle, then what we do over here is we give each of the particles that bumped into another particle a random kick. We move at some distance that's, say, comparable to its radius, or some finite fraction of its radius. simply repeat the process. So that's all there is to the simulation. There's nothing else happening. Basically, the idea is that if the particles get too close, that they collide in some way, and that this leads to small irreversible motions. So here what I'm showing you is the results of two simulations, one for a strain amplitude of 2 and one for a strain amplitude of 5. The particles, if two particles during a strain cycle happen to bump into each other, we color them red. And of course, I'm just showing you here the stroboscopic part of the simulation again, so you see the particle positions once per cycle. Now the thing that's interesting is that this low strain, the number of particles that bump into each other decreases with time, whereas at the higher strain, it seems to go to some finite fraction of particles that are bumping into each other. And in fact, if you wait long enough, you find out that over here, for the low strain, all the particles manage to find positions through this process of random displacement such that they no longer bump into each other. Whereas this one heads towards a steady state. So we call this process random organization, in that this system, over here, has organized itself through these random motions that result from collisions into a state such that collisions no longer occur. Now, if you plot the fraction of what we call active particles, that is, particles considered active if it moved in the last cycle. So if you plot the fraction of active particles as a function of time, if you're above a certain threshold, it looks like this, and you see that it decreases initially, but then goes to some steady state. On the other hand, if you're below some threshold, it decreases fairly rapidly and eventually goes to 0, and then the system stops evolving and becomes reversible. Now, one interesting thing is you can look at this final steady state value of the active fraction of particles, and what you get is a plot that looks like this. So at high strain amplitudes, it goes to, you can have something like 80% of the particles being active. As you go to lower and lower strain amplitudes, eventually that fraction falls to 0. And if you look at this, it looks a little bit like a phase diagram, something you might get out of an equilibrium system. But of course, the thing to remember here is that this is a completely non-equilibrium system. There's no temperature, there's no free energy, there's nothing like that. You just have a completely non-equilibrium system that's organized itself into this state. Now, a couple of comments. One is you can fit this curve to a power law. It is gamma naught minus gamma naught C, where gamma naught C is the critical strain amplitude right here. Another thing to notice is we can fit these curves to this functional form. So the important part to notice is that what you get is you have here an exponential with a time constant tau over time to a power. So what this means is that near the transition near this transition here, you get a power law behavior in this decay, and far from the transition, you get an exponential. This is inspired simply by analogy with equilibrium critical phenomena, for those of you who might be familiar with that. So then what we can do is we can use this fit to measure this time constant tau. By the way, alpha is the same. It's the same for all curves. We don't adjust it. We use one single value. But tau varies from strain amplitude to strain amplitude. So here we have a measure of it. And if we plot tau as a function of the strain amplitude, what we find is that this equilibration time diverges at the transition, at the critical strain amplitude. So again, this looks an awful lot like equilibrium critical phenomena. And again, you can fit this time constant to a power law, as we've done here, both above and below the transition. Okay, so it looks like what we have, at least in the simulation, is some kind of non-equilibrium critical phenomenon, a non-equilibrium phase transition. So then the question becomes, is this what's really happening in our system? So with these simulations in hand, we went back to the system and did the experiment in a little different way that allowed us to test some of these ideas. So here what we did is we used the same Couette cell, the same particles, but this time we introduced into the fluid a dye. And then we illuminated the fluid in a different way with a sheet of laser light that came in like this and went through the sample like this. So you illuminate a plane within the sample and then view it through a camera that filters out the scattered light so that all you look at is the fluorescence from the background fluid. And so what you see then is the particles appear as dark circles on a bright background. And then what we can do is we can follow those particles and you can see how they move around in time when we shear it back and forth. So we do the same trick again. Namely, we track the motion of each particle stroboscopically. We look at it at the same position in its cycle. So what we show you here is this is above the transition, this is below the transition. You can see we've gotten better now. This is with the dyed spheres, this is with the fluorescent liquid. And here you get reversible behavior, here you get irreversible behavior. Now, what we've done here is we've taken these pictures and digitized the positions, the stroboscopic positions both below and above the transition, and we've colored the particles according to how far they moved in their previous cycle. So the ones that are colored black have moved a lot. They moved about 40 microns. Remember, they're about 250 microns in diameter. The ones that are colored white haven't moved at all. All right, and so after cycle 1, you can see that most of the particles are fairly dark, meaning there's been a lot of movement. And as it goes, actually we're doing this side first, sorry. And this is above the transition, so actually let me back up. And you can see that the particles remain pretty black, meaning that you're getting large movements of the particles. Over here below the transition, we do the same thing. You see that it very quickly becomes rather white, and all the particles stop moving after a few cycles. If you plot up the mean square displacement for one cycle of the particles as a function of time, you get curves that look like this. So far above the transition, you see just a short decay, and then it goes to some steady state value. As you get nearer and nearer the transition, you can see that the amount of motion, the random motion that the particles undergo, drops by several orders of magnitude. All right, and this down, by the time we're down here, we're essentially down to the resolution of our camera. These data, again, can be fit to the same functional form that we use in the simulation, namely a power law, exponential divided by a power law, where the same power is used to fit all the samples. Now, we also, in the course of this, discovered a more accurate way to measure this. It turns out that the outer phase, it turns out that the viscosity, both the in phase and outer phase, increase at the reversibility threshold. And the outer phase viscosity is particularly sensitive since for a Newtonian fluid you expect that to be 0. As you go through the transition, it rises dramatically, you can see here, by a couple orders of magnitude. And this actually allows us to follow the irreversible behavior. So here, what we plot is the outer phase viscosity as a function of time, and we find that above the threshold it decays a little bit and then goes to a steady state value. And as you go towards the threshold, it decays much more. And again, you can fit it to this same functional form of an exponential over a power law. So then again, you can extract the time constant there, and you see that the relaxation time as a function of strain amplitude does indeed increase by more than 2 orders of magnitude as you go through the transition. So it looks looks like in the experiments we're seeing the same kind of phenomena that we saw in the simulations. That is, we're seeing a non-equilibrium phase transition. You can plot up the data to get the same kind of power law behavior. Now, I'll show you something a little bit different, or another phenomenon you can see with these systems, where we add in sedimentation. So what we've done here is we've prepared exactly the same system, but we've prepared them in such a way that the particles are no longer exactly neutrally buoyant. In fact, we've made the fluid a little less dense so that without any shearing, the particles will settle to the bottom of the cell. And then we shear them back, shear the particles back and forth. And in fact, that's what we're doing here, just a second. Oh, I know what I want to do. I need to, this movie is actually in real time, so I need to speed it up and show you what happens. So what we do here is we actually increase the strain amplitude slowly. And as we increase the strain amplitude, what you see is that the height of the particles increases. So there's a balance between shear-induced diffusion and gravitation. As we increase the strain amplitude more, it goes up even higher, like this. All right, so what we can do then is we can look at the density of particles as a function of height. So here we have density, and here we have height for different strain rates. And what we see is we get essentially flat densities. This is at a lower strain amplitude, this is a higher strain amplitude, and this is a still higher strain amplitude. And if you plot this up, if you plot up the volume fraction of spheres as a function of the strain amplitude, you get curves that look like this. We can go and we can do the same kind of simulations again. So what we do here with these simulations are just like before, except we add in sedimentation in a very simple way. Namely, what we do is at every cycle, we make every particle fall by some small amount. And what you can see is that as you start shearing it, you get a balance between two currents. You have a downward current due to sedimentation, and then you have an upward current due to the shear-induced diffusion. When they match each other, you get a balancing in the motion. Now, one thing that's fundamentally different here from the other situation is that you never go to a state where the system is completely inactive. Because if it were completely inactive, particles near the bottom would fall to the bottom, they'd then stop, and then other particles would come fall and hit them and start and reactivate them. So there's always some new activity being created at the bottom of the cell. And it's that new activity that's created there balanced with it dying out as the system diffuses upward that leads to a steady state. Now, if you look at this, oops, press the wrong button. All right. There we go. You can see that here's our density profile. At very low strain, high strain, you get a constant density profile with a flat top. At lower ones, you get a somewhat flat top followed by a more or less exponential tail here. Now, if you plot up the volume fraction, say at this top portion, as a function of the sedimentation velocity, which we vary by changing the density, you get a bunch of data that looks like this. So this is for various straining amplitudes. In order to figure out what's going on, you can do a little scaling argument. If you say that the mean spacing between particles is c here, and the height is h, then when it sediments a distance c, that defines a sedimentation time tau x. All right, so tau x is the time it takes particles to sediment one interparticle spacing. You can then define So what that does is that creates a dense layer at the bottom where particles collide and create new activity. The only way you get rid of that activity is for particles to diffuse all the way to the top. That defines the diffusion time, which is h squared over 4d. So then what you can do is define this dimensionless ratio A, which defines the competition between diffusion and sedimentation. So it's the diffusion time over the sedimentation time. So then, if we take our sedimentation velocity and write it in this non-dimensional way, so A is essentially a non-dimensional sedimentation velocity, you see that all the data fall on a single set of curves. And so for A less than 1, you have that particle density goes to the critical particle density, and for A greater than 1, then the density increases. So what you can do with the data, or with the simulation, is you can follow a given cluster. So here you have a cluster that's just been created down here at the bottom. You had one that was quiet, and another one came down and hit it, and then this nucleates a new cluster. And then what you can do is follow that cluster in time. It could disappear on the very next step. That is, the very next step, these two could separate, then that would be done. Or they could keep colliding, and they could excite a few more, and the cluster would grow bigger. But eventually, that cluster will die. So here is an example of a fairly long-lived cluster. We plot here the x position versus the y position as a function of time in the vertical axis. So we create the cluster down here, and we follow all its descendants as a function of time. We find that it comes up here. This part of the cluster eventually dies, but this one continues on. So finally, the entire cluster that was created at time 0 dies, and that defines a cluster lifetime. If you plot up that cluster lifetime and against the number of clusters that have that lifetime, you find out that you get a power law that it goes as t to the minus 1.2. You can also define a cluster size, which is just the total number of points in this, that also goes as a power law. This is, in fact, the hallmark of a self-organized critical state. And so what we have here is it means that in this region up here, the system all by itself, when you get to small a, adjusts its density so that its density is equal to the critical density, where you have this balance between diffusion and sedimentation. This is the same critical density we saw in the equilibrium phase transitions. So, you get this self-organized critical state. Now, I'm not sure, let's see how much time I have left, maybe just a couple minutes, so I won't spend too much time. What we're working on now is this random organization in the suspension of rods. And so I'll only give you a little bit of an introduction to this. It turns out to be very interesting. We do the same thing, but this time we use rods. And the rods we actually use are little pieces of nylon fishing line that we've cut into about 1.5 millimeter lengths, about 1/10 of a millimeter in diameter, so they have an aspect ratio of about 10 or 11. The overlap concentration for this, by the way, is about 1%. So then we do the same thing, and what you see is you see these sort of irreversible motions when you shear it back and forth and look at it stroboscopically. So we can do the same sorts of experiments we did before, and we can follow these motions either through the viscosity or through looking at them directly. And what we find is that there's a particular state, so this is, I believe, is a concentration of 15%. We've done it for 5, 10, 15, 20%. And you get a critical state just like we did before, and if you look at it, you see that the mean square displacement, or eta double prime, decays as a power law here over about 2 decades. Below, these are the data for lower amplitudes, and you can see that the mean square displacement is headed 0. At higher amplitudes, they start to level out, but then they start going down again. Here's a huge amount of data. We can try, and it looks, if you look at it, it looks superficially like this, at least at the lower strain amplitudes. What you can do, a little bit more sophisticated analysis, is to look at the active fraction and scale it according to the scaling law, which goes as gamma minus gamma c to the beta times some function of time times gamma minus gamma c to the eta. And the criticality, this should reduce to t to the minus beta over nu. In fact, if we try to collapse our data in this way, we get very good collapse for gamma below gamma c with these critical exponents. If we try and do it for gamma above gamma c, we should get something that looks like this, but in fact we get something that looks like this. I think just in the last couple of weeks we've come up with an explanation that works quite well, but it probably takes another 20 minutes to explain, so I won't go into it. I will just suffice it to say that what's happening here is that the rods are orienting with time. That is, you start out with the rods with random distribution of orientations, but at these higher strains, the rods start to orient. And they orient in a funny way. If you shear them like this, they orient in the vertical direction, what we call a log rolling mode. And what that does is it decreases the chances that two particles will collide with each other. You can see if they're unoriented like this and you shear them, they're fairly likely to hit each other. But if they're all aligned like this, they're much less likely to hit each other. So in order to understand what's going on here, we have to take into account the fact that the orientation of the particles is changing with time. You can see up here, there's one at long times where the particles are pretty well oriented in the vertical direction. If you take that into account, you can understand this in the same framework that we understood the spheres. But I'll have to stop here because I think my time is up, and I'll just take any questions that people might have. Okay, and I should mention that a lot of people involved in this work. This started with Jerry Gallo, who was visiting my lab in UCSB. John Brady and Alex Jashansky did some hydrodynamic calculations, which I didn't have time to tell you about. Of course, I told you about Paul Chapin's model in the simulation. Laurent Corte probably took most of the data I showed today, along with the fiber work, which is done by Emma Filippi and Alex Branch's team. So with that, I'll take any questions.
Yeah. In the simulation, when you described the collision of particles, you said that they would just bump off in the random direction. Is that right?
You're right.
Did you try to do some deterministic
Yes,
collision?
and that changes things dramatically. If you, for example, make the particles, when they fly, go in opposite directions, or just go along the line that connects them, you find that they self-organize very, very quickly, and in some cases even go to a more or less crystalline state at high densities. So it's a very different process if those collisions lead to displacements that are not completely random.
So did you observe in the simulation anything like what was an experiment when the collision is deterministic?
What do you mean the collision is deterministic?
Well, not the collision. The calculation of the collision is somehow deterministic, but not random.
Okay, maybe I'm misunderstanding, because I thought I just answered
the first question that I asked was whether you try to do calculation without random displacement at collision.
You have to understand, they collide. That, whether they collide or not, just depends upon their positions.
Yes.
And so, while their positions, maybe you don't know what they are, everything else about that is deterministic. Once they collide, the part that isn't deterministic is when you go back to the system, to the original positions, you give them a random kick that can be in any direction. Like I said, if that kick is not random, it tends to lead to an absorbing state that is a reversible state always, or up to much higher densities than what we observe experimentally. At these higher densities, in fact, the system crystallizes.
So there's no diffusive motion in that case.
There's no diffusive motion.
So, well, then, like to continue the question. First, you say that there shouldn't be any diffusion in the system, right? Well, due to Stokes equations. And then you observe, but though you observe it in the experiment. And when you do the simulation, you say, well, we'll just add the random force just because we see it in the experiment.
Well, so no, the idea that the simulation is trying to capture is that if two particles get too close to each other, that they interact in some irreversible way. And in fact, there's experimental evidence for that. There's a number of things that can lead to irreversible motion. Hydrodynamics all by itself cannot. There's, for example, some indication that if the particle surfaces are rough, then they can actually come in contact with each other. And if they come in contact with each other, physical contact, then you no longer have purely hydrodynamic interactions and some sort of friction possibly. You have van der Waals interactions, but these lead to, we believe, the irreversible displacement. So it's these very, very close encounters. So the simulation just says, look, if particles get too close, we posit a irreversible interaction without knowing what it is. Experimentally, it seems to be that the particles actually contact each other, and this physical contact leads to these irreversible motions.
Thank you.
Yeah.
So, if you took the viscous liquid out, it would essentially be like a granular kind of system, right?
Right, except that you have to do it in space so that you don't have any gravity.
Yeah, you could. Yeah. Well, no, I mean, we'll do this, right? They put sand in a thing and they shake it around.
Right, but you have a very different situation there because you have gravity always trying to pull.
But I was just curious, I mean, is there sort of a connection between the reversibility of granular systems and what you're seeing here? I mean, you've got, people think of your reversibility coming from a coefficient of restitution or something like that, right, where you're dissipating energy.
I don't see any simple way of making a connection. It's true that in certain granular systems, where you have gravity acting, if you strain the system back and forth, you can get it eventually to trace out some sort of at least rheological curve that is reversible. Whether the motions of the individual particles inside the system are actually reversible, I don't believe it's been measured, but I doubt that they are.